Good afternoon, grade 11s. I trust you're all well and that you're surviving the lockdown and that you're doing your schoolwork. Before we commence with the first presentation on gases, I just want to refer you to Psalm 91, verse 10 and 11, and that is my prayer for you. So if you want to go and read that at home, that would be good. Right, well, first of all, the concept of ideal gases. The question came to me, I posted this and put the photographs of the textbook of the relevant pages, and one or two people inquired about the ideal gas. Now, the ideal gas is an imaginary gas. It is a model built by scientists to predict how gases should react under certain conditions. Now, the ideal gas model is there, and then we can compare the actual behavior of real gases and compare that to this ideal gas model. So that's all it is. It's on page 161. You can go and read all about the behavior of ideal gases. That is what scientists expect an ideal gas to behave like. And we can, as I say, we can compare the behavior of real gases with the ideal gas model, and then we can say, yeah, real gases behave as ideal gases should behave. Or we can say, real gases behave like ideal gases under certain conditions, but sometimes the behavior of real gases deviates from the behavior of ideal gases. So that's just in short. We'll come back to the concept of ideal gases and real gases and have a few examples of where the deviations are, and I'll show those to you. So right, there are four variables when we talk about gases. You know about the kinetic model, about the movement of particles, that they're far apart in gases, that they exert pressures on the walls of a container, etc., etc. That's all summarized there for you. But there are four variables which are important when we talk about gases. And one is pressure, the pressure on a gas or the pressure exerted by a gas. There's the volume of the container which contains the gas. Then there is the temperature at which this gas is, and then the amount of gas or the number of moles of gas in the container. And when we consider these four variables, they will be in relationship to one another. When the one changes, the other one might change. So what we want to do is to examine the relationship between different of these variables. And the first one we want to examine is, what is the relationship between pressure and volume of a gas? And if we want to examine what the effect of an increased pressure on the volume of a gas is, or what the effect of a decreased volume is on the pressure of a gas, then we need to keep the other two, temperature and amount of gas, constant. So those are the control variables, they're the constants. And the scientist who designed an experiment to investigate this relationship was called Charles Boyle. And what Charles Boyle found, and I want to just give you a brief illustration. If you took a syringe and it has a plunger at the back and it has an opening in the front, and it is filled with air, and you closed the opening in front and you pushed the plunger at the back, you're increasing the pressure on the enclosed air or gas. What happens to the volume of that gas? I mean, we all know when you use a bicycle pump, you can close the front and push at the back, you know the pressure increases, but because the plunger is going in and the volume of the enclosed gas will get smaller and smaller and smaller as you increase the pressure. So what he did was he examined this. There was an apparatus that he designed, which we will talk about in the next session, but I just want to give you the mathematical relationship between the pressure and the volume of the gas. What Boyle did was he increased the pressure, and he found that increased pressure will lead to decreased volume. So pressure and volume are inversely proportional. He did a whole lot of readings, and he found that there's a proportion here, that the more you increase the pressure in the same ratio, the volume will decrease. So pressure is directly proportional to the inverse of the volume, or then stated otherwise, pressure is inversely proportional to volume. Tell me, does this mean the same thing? Volume is inversely proportional to pressure. It's exactly the same thing. So whether we look at it this way or that way, it boils down to the same thing. So we know that we can convert a proportion into an equation if we include a constant. So we can say, and this is called the gas constant. This proportionality constant, so we can say that equals a constant times 1 over V, or P equals a constant over V. Therefore, PV is a constant value. So that is Boyle's law. Now, on a graph, when Boyle was doing this experiment, he found the following, and that's how he could come to this conclusion. He found that if you put pressure, you increased pressure and checked what happened to the volume. This was what he found. That means as the pressure, at a high pressure, you've got a very small volume. And as the pressure decreases, the volume will increase. Or otherwise, as the pressure increases, the volume gets smaller. And then if you calculate the inverse of the volume against pressure, you will find that proportionality, and that's what gives us this. Pressure is directly proportional, or inversely rather proportional to volume. So what this means is that if you have an enclosed gas at a certain pressure 1, it will be at a specific volume 1. But the value of P times V will be constant. That means that if I increase the pressure to P2, there will be a new volume, V2. But the product of P times V will still be a constant value. So that means that PV, P1V1 equals to P2 V2. And that is the first gas equation, and that is Boyle's law. So that is just the basic of Boyle's law, and I think I'll give you an exercise. What you could do for me is on the textbook, I'll go and photograph it and send it to you. On page 164, there's an example and a solution, and we can talk about that tomorrow.